Hey everybody, Dr. White here with some R applications involving conditional distributions. So here we are in our studio, and I've got an old R script here that I can just close out of. Got a nice empty global environment. Noticed I've restarted my R session recently, so that's good. Start back at square zero. Let me go to the common folder and pick out an R script, section 4.3. And what I'd like to do is to just play around with that mixed distribution that we did as an example by hand, the one about the random Shire inhabitant, where the Shire is inhabited by Hobbits and also a little bit by ents. So remember, the premise is 95% of the Shire population are Hobbits. Let me make that a little bit bigger. 5% are ents, okay? And the height of a random Hobbit would be normally distributed mean 40, standard deviation 5, whereas a random ent would have a mean of 200 inches height, standard deviation 20. And so let's say you take a Shire inhabitant at random. Let's say the height of the person selected is called capital X, totally decent random variable, mixed distribution. So what I'd like to do is get some estimate of what the probability density function for X would look like. And the way I'm going to do that is just try the random variable a whole bunch of times and then make a density curve of my results. So like say I'm going to try 1,000 times. Let me run that command. N is 1,000. And what I first need to do is my conditional work. I'm first going to figure out if the person I pick is a Hobbit or an ent, and then depending on what they are, I'll throw a height out. Okay. So I'm setting up a little vector here called type. Okay. And it's going to be the result of this call to the sample function, which if you've not had CSC 115, this might be the first time that you've met it. No, maybe we talked about it earlier. But what I'm going to do is I'm going to grab randomly from this little vector of two words, Hobbit and ent. And I'm going to grab n equals 10,000 times, size is n. Every time I pick something, I'm going to stick it back so that, like I'm always, every time I grab, I'm looking at two things I could get. And the chance of grabbing Hobbit is 95%, and the chance of grabbing ent is 5%. That's what this little, that's what that argument is doing. So I'm going to run this. And there's type over in my global environment. So, mostly that's going to be Hobbit, but sometimes it's going to be ent, on and on for 10,000 times. Now, I'm now going to make a vector of what should be the mean height for my creature, each of my 10,000 creatures. If the creature is a Hobbit, the mean should be 40. If the creature is an ent, the mean should be 200. There's a great way to make these means. It's the if-else function. The first thing you give to the if-else function is a little conditional, a little statement that either comes out true or false. And then when it comes out true, you stick in this first value. And then when it comes out false, you stick in the second value. That's how the if-else function works. 3 arguments. The first argument is something that comes out true or false a bunch of times. And then this is what you stick in whenever you get a true. This is what you stick in whenever you get a false. So like if I were to just run just that little piece, so I've got that selected and I say Command Enter, you see there's like 10,000 trues and falses there, okay? And every time there's a true, I'm going to put in 40. And when there's a false, I'm going to put in 200. Let's go ahead and make this. So my vector means here is a bunch of 40s and 200s. It's mostly 40s. Now, standard deviations works the same way. If my creature is a Hobbit, standard deviation needs to be 5, otherwise it should be 20. Okay, so now I got these SDs. It's mostly 5s and some 20s. And now I'm ready to actually try out my random variable x. I'm going to use the R-norm function to get random normals. And I want the n is 10,000 of them. But here's something cool. For mean, you don't have to put in just one single number. You could put in a whole vector of numbers. And so I'm putting in a vector of 10,000 numbers, the means vector. Same for SD. You can put in a vector of numbers. It's just that these vectors here that you stick in have to have that length for this to work. And so what happens is 10,000 times it's going to grab a normal random variable, but sometimes it's grabbing a normal 40, 5, and sometimes it's grabbing a normal 200, 20. Ready, go. And it happens almost instantaneously. So here are my sims, and you can see starting off, it looks like it's all Hobbits, around 40 inches high. But there are going to be some, things around 200 inches high, which are the ents. Going to make a data frame whose only column is those sims, and that column's called X. If I popped it up there, there it is. I'm calling it X just because capital X was our random variable, so here are some possible values, little x. And I need to load the ggplot2 package because I'm going to make a graph. Okay, I got it loaded. And I'm going to make one of these density plots with a rug on the bottom in the way that we've learned before. Again, that's something you don't have to pay a lot of attention to if you haven't had CSC 115. I'll always provide the code you need. But if you've had CSC 115, study it, review it, think about why it gives what it gives. And so I'm going to get my face out of the way and check this out. It makes total sense. So this density curve is an estimate of what the PDF would look like. And sure enough, most of the density is somewhere here around a 40, but there's a little bit of density over here around 200. About 5% of the total area is here, and about 95% of the total area is here. The rugs, it's a little bit hard to tell here because there's so much overplotting, but like about 9,500 values are here, and only about 500 values are around the 200 inches. So the PDF would basically look like a little two-humped thing, a hump here and then a little hump here. And that's how PDFs for mixed distributions will often look. You'll often be able to separate them out like that, sometimes not. Just for fun, why not write a function that can do all this work for you really fast? I call the function ShireSim. And it's built using the reserved word function. And you say what the variable for the function is. N is going to be like how many simulations you want. And then you do that same work of getting the type, the means, the SDs, and the sims. And then I'm going to return two numbers. I want to return the mean of those simulations, because that would give approximately the expected value of the random variable. And there's another function here called var that computes something called the sample variance of a list of numbers. And it's intended to estimate the variance of the distribution those numbers come from. So I won't talk about how var works yet. That's going to be a chapter 5 discussion. But I am going to return those two numbers. The first one I'm going to call EV, and the second number I'm going to call variance. And they're going to come two numbers in a list. And so I'll go ahead and define that function. And now I'm going to try that function where n is equal to, what is that? 1, 2, 3, 4, 5, 100,000. So I'm trying 100,000 times this time instead of 10,000. And check it out. the average of my 100,000 tries is really, really close to the expected value for X that we calculated back in the previous screencast. It's really close to 48. And remember that the variance was like 1259.75, was it? And look at this. The estimate of the variance based on these 100,000 tries was pretty close to that. If I tried 1,000,000 times, let's see what it would be like if I did it 1,000,000 times. Takes a tiny bit longer, but I come even closer to the 48. Well, no, not even, not actually, I came a little further away. And I came a little closer to the 1259.75. Let me try that one again. Let's try 1,000,000 times again. And I got really super close this time. And again, really close to the variance. So that's how you would do simulations with a mixed random variable. You would have to first figure out what is that, how the mixture ought to go in the simulation, and then you got to find a way to get the different actual values of the random variable based upon your knowledge of the mixture. And it was just a cool thing that our norm lets you do this vector stuff with the means and the standard deviations. That you're not always so lucky. Well, anyway, I'll go ahead and save these changes, and I'll close this file out, and I'll clear up my global environment, and hey, I'll even restart my R, and I'm back at square one for the next time that we go back home, get together. See ya.